Mr. Bhaskar, sir, from Canada. Are you here, sir? Oh, there you are. The title of his presentation is Canadian Nuclear Laboratories, specifically the Thoria Roadmap Project. Dr. Bhaskar, sir, is the Director of the Nuclear Science Division at Canadian Nuclear Laboratories in Chalk River, Ontario. Sir, as he's commonly known, obtained a Master's in Physics from the IIT Kanpur and a PhD in Physics from the Ohio State University in Columbus, Ohio. Sir has broad research interests in nuclear science, particularly in nuclear instrumentation and in neutronics and neutron beam experiments. Sir, the floor is all yours.
Thank you. I have to tell you that I just flew in last night, and it's about 4 or 5 in the morning, my body time, so if I'm a little bit dazed and confused, I hope you'll excuse me. So I'm going to talk about the Thoria Roadmap Project. It has nothing to do with ADSs, which is the subject of the session, I suppose. So what I'm going to talk about is the use of thorium in the Canadian pressurized heavy water system, which we like to call CANDU, the CANDU system, which is very similar to the Indian pressurized heavy water system. Canada has a rich history of irradiating and studying thorium. W.B. Lewis, who was the founder of the one of the founders of the Canadian Nuclear Laboratories, which was called Atomic Energy of Canada Limited in the day, realized the potential of thorium utilization in heavy water reactors very early. And when the NRX reactor went online in 1949, there were already thorium metallic clad fuel rods in the blanket, used as a blanket in that reactor. So consequently, there have been many types of thorium fuel that have been studied at Canadian Nuclear Laboratories. They are listed across the top there: oxide, thoria, thoria urania, thoria plutonia, and thoria with U-233 oxide. All of these we have put them through a zero power reactor, which is currently called Z2, to study the reactor physics. At low power critical experiments, they have been tested, there have been irradiation testing done to more than 50 megawatt days per kilo of heavy element in NRU. These were done in the NRU fuel rods in the early days and the loops later on, as well as in the nuclear power demonstration reactor, which is NPD, and in the white shell organically cooled reactor, which is WR1. The carrier for thoria has been CANDU fuel bundles, 28, 37, 42 element bundles. The pellets, which are shown in the picture on the upper right, and the elements have been fabricated in both the CANDU Advanced Fuel Lab, which is called the CRAFT Lab, and also in the Recycled Fuel Fabrication Lab at CNL, which is the lab that we use for handling plutonium. There have been extensive development and execution of techniques for post-irradiation example ceramography, fission gas release. In fact, at the bottom right is a picture showing fission gas release experiments in a fuel string that was irradiated with the highest bundles going up to well over 50 kilowatt hours per megawatt days per kilo. There have been thorium fuel reprocessing experiments at White Shell Labs in the 60s and 70s. And of course, there have been lots of studies of advanced fuel cycle systems and concepts over the years. There's an alphabet soup there at the bottom. OTT stands for once through thorium cycles, starting with the very famous paper by Mike Milgram, lately by Blair Bromley. Self-sustaining thorium cycle is the SST. There has been the concept of the advanced fuel cycle reactor, which is the AFCR. And lately, we have been studying the supercritical water reactor as part of Canada's contribution to the Gen 4 project. That is also, the reference fuel for that is thoria, 19% plutonia. So all this is to say that we think that the pressurized heavy water system, CANDU system, is ready for thorium. And that's really what this talk is about. The Thoria roadmap project at Canadian Nuclear Laboratories looks at the gaps that need to be filled in order to actually put Thoria fuel in a CANDU reactor or a CANDU type reactor in the short to medium term. On the right-hand side, you see various elements of the pressurized heavy water or CANDU reactor system. The fuel carrier is the fuel bundles, where the fuel is in pellets inside fuel pencils. That's the middle picture on the right. The fuel bundles are contained inside a pressure tube and a calandria tube. That's at the bottom, and the whole thing is in a lattice immersed in a low temperature, low pressure, heavy water calandria, which also contains the reactivity devices, and that's at the top. And sort of the left-hand picture, the graph, shows the kind of reason or the motivation for putting thorium or thoria into a pressurized heavy water reactor. It's from a recent paper published in the ANS Nuclear Science and Engineering journal, and it shows the fissile utilization relative to natural uranium for various scenarios where thoria urania, that's the upper set of plots, and thoria plutonia are used in a pressurized heavy water reactor. And you can see that in the best case, you can get an advantage of two. That is, you can produce twice as much energy from the same amount of initial uranium if you used a certain scenario of thoria in the fuel. A more realistic, perhaps, is a utilization about 50% higher than what you would use with natural uranium. So for a region or a system that is short on uranium, putting thoria is a great way to sort of extend the amount of energy that you can get out of the limited resources. So it is in this context that we come to CNL's Thoria roadmap project. The CNL's Thoria roadmap project has really started in 2011 when we decided to get together and do take a good hard look at what exactly are the barriers or the challenges to putting, or the gaps as we like to call them, to putting thoria in a reactor in the short term, into a pressurized heavy water reactor in the short term. And so there was a lot of literature within Canadian Nuclear Laboratories, formerly called Atomic Energy of Canada Limited, and open literature, papers, about 3,500 papers were looked at, and all the gaps were identified and classified into sort of these 11 key science and technology areas. And these range all the way from fabrication technology for fuel to irradiation testing, materials properties that are missing, modeling, doing fuel safety experiments, reactor physics, of course, radiation protection, waste management, reprocessing, thoria, the supply chain, and including non-proliferation and safeguards. And in this talk, I will try to address some of these. As you can tell, this is a vast area, and I don't think there's any single person that's an expert in all of these areas, so I'll be giving a bit of a non-expert view. And I'm fortunate that I've got our chairman, who also worked at CNL for many years, who can probably help out if there are sticky questions that I don't know the answer to. So starting with the first area, which was fuel fabrication, there has been a lot of experience and success in thoria urania pellet fabrication, not as much consistency in thoria plutonia pellet fabrication. So for doing pellets, what we find is that we need fuel specifications, especially impurity specifications, and we need fabrication procedures for controlling the grain size. Experience indicates that there's a large variability in the processing behavior of thoria, which depends on their source. So we need more in-depth understanding of minor impurities and morphology of powders and their effects on processing. And the goal, of course, is to reliably and consistently utilize thoria powders from a variety of sources in order to make fuel that behaves well under irradiation. One of the issues, as this slide shows, is the diffusion of plutonium in thoria. And this just shows a picture of the line. Even the fabrication of thoria, I'm told by the experts, even the fabrication of thoria with uranium is different than the fabrication with plutonium and is different from other actinides. And most likely, impurities affect the diffusion or the surface of powders to a greater degree for thoria than they do for uranium. So that, in a nutshell, is sort of the gaps that we have with fuel fabrication. Irradiation testing and post-irradiation exam is the second gap area, or the science and technology area where we have a gap. And we have a lot of irradiation testing experience in-house at Chalk River. And of course, the Indian program has a lot of experience in thoria irradiation in heavy water reactors. What I've shown here is at Chalk River, we have probably irradiated thoria to more burn-up than anywhere else, probably in the world. What we have shown here is irradiation history of a thoria plutonia fuel string with the maximum irradiation going out to almost 50 megawatt days per kilo HE. That translates into 50 gigawatt days per ton of heavy element. There are some curious things in this picture. For instance, above 30 megawatt days per kilo irradiation, there are some spikes which we don't understand in the linear power, and those seem to be correlated with an increase in fission gas release. So CNL has also performed several other long-term irradiations. Much post-irradiation examination has been done, and much of the material is archived and is being used for ongoing and future post-irradiation examination. One of the curious features in fission gas release from that particular experiment, if you look on the right-hand side, you'll see that the fission gas release was very low for the first 3 bundles, but for the last 2 bundles at the higher power, it was very much higher. And this is sort of the mystery for this particular irradiation experiment, and it points to the fact that we need more irradiation experiments to fully understand what is going on. And in this particular case, here is a micrograph of the fuel, and it is thought that that small initial grain size gave rise to the high fission gas release and high burnup in this case. So this points to the necessity of the gap here is that we need repeat irradiations to support a wide variety of possible compositions of the fuel. In addition to grain size, homogeneity, and fission gas release, there is a long laundry list of issues regarding thoria irradiation and post-irradiation exams. We need irradiations in neutron spectra, which are characteristic of thorium reactors. We need to study the microstructure evolution with irradiation, burnup, and power. We need to understand the effect of power ramps. We need to understand how to detect other species than in urania, for instance, protactinium-233. Ceramographic techniques for thoria are very different than urania, and we have done some work in developing those. We need codes and models to handle thoria. N-flux peaking is much more important with the high fissile content in some of the thoria bundles. And of course, we need standardized measures for burnup, for measuring burnup of thoria bundles. Number 3 on the list was material properties. So material properties is key, of course, and a lot of work has been done around the world on measuring material properties for thoria, both for unirradiated, but also for irradiated materials. We also need, but more needs to be done. And I'm told that especially what we need is we need to measure material properties for high temperatures, that is under accident conditions. So while material properties have been measured under normal operating conditions for very high temperatures approaching 2000 degrees, very little is known. And that is an area where CNL is working on. We want to show you this laser flash apparatus for thermal diffusivity measurements, which I'm told is only one of 3 in the world. And we have got one of these at Chalk River over the last year or so. It has been benchmarked against thermal diffusivity measurements done at ITU in Germany. And here are some recent measurements for urania. And of course, these will be also carried out with Thoria. The next topic is modeling of Thoria fuel. Measurements, as you know, need to be incorporated into validated models to be useful for exploring fuel design and behavior. Existing fuel models for urania do not work well for Thoria. And what we have got is a new approach used in the US and elsewhere, computational thermodynamics modeling. And we have started doing this at Chalk River as well. Here are some details of a recent model. I'm not going to read all the details here because I understand very little of this thermodynamic modeling. But I'm told this is good stuff, that this is cutting edge, good stuff, and it reproduces data extremely well. So it reproduces, it predicts experimental oxygen potential and phase diagrams with very good agreement. And here's an example of oxygen potential in a ternary system. And you can see that the data points which have been measured independently fall right on the lines, which are the predictions of the model. So even so, the modeling is lacking various things, and there's again a laundry list of effects that need to be included and need to be predicted by fuel models. And here's the laundry list out there. You can read it yourself. Ultimately, we are interested in producing codes that predict the behavior of Thoria fuel, including defected Thoria, prediction of fission product released to coolant. Some experimental work in NRX from the NRX days exists, which shows that there is 10 to 100 times less fission product release when there's a defect than with urania for Thoria. We need to model the effects of microstructural variations on behavior, the effects of neutron flux depression, and of course grain growth, densification, swelling, pellet cracking. All of these we need to have models in order to advance to the point where we can do routine irradiations. Fuel safety. So once again, there is a list of items, details, if you will, that need to be measured in order to make the case for safety. We can also add pellet and pellet cladding interactions to this list. There is I'm told very little data on measurements with defected fuel, if you will. There is existing data from an experiment in the NRX reactor, which had a fission product monitoring system on the fuel irradiation loop, unlike NRU, which does not. So we have that data, and there were some fuel defects for which we have data, and this data needs a lot of further analysis. And I'm told that even the assumption that the fuel product release is bounded by urania may not hold true for mixed oxide Thoria fuel at high temperatures. How much time have I taken?
You're good.
On to reactor physics and fuel cycles. There has been a lot of work done recently on optimizing, finding the best fuel bundle and core concepts. And you can see the paper that has been recently published in the ANS Nuclear Technology Journal. There have been other papers also recently from Blair Bromley and his colleagues. And this is in line with a long series of papers that have come out of Chalk River on thorium utilization in heavy water reactors. There are various fuel bundle configurations on the top and various seed blanket designs, both homogeneous and heterogeneous, that have been studied. And I showed you the results of one of these studies right at the beginning of the talk. We need to continue to make these studies in order to figure out the best way of utilizing thoria in a pressurized heavy water reactor. As far as physics goes, as you know, we know a lot about physics of uranium in pressurized heavy water reactors. The current libraries in the codes are known to be poorly adapted to thorium-based fuels. On the left-hand side is a cutaway picture of our zero-power critical facility called Z2. This is where, of course, experiments, all of the CANDU lattice physics experiments have been done in Z2 in Canada. Also, a lot of the thorium experiments have been done in Z2, and we have those experiments, and we continue to analyze them, in addition to getting new experiments done. On the right-hand side, you see the sort of code-to-code comparison that shows that the current codes that are being used for the uranium systems are not really well suited. There's a K infinity versus burnup modeled via Serpent and via WIMS AECL, and there's a large sort of 10% of the order of 10% discrepancies, which are certainly not good. So all those will need to be addressed. There is a lack of critical benchmarks for unirradiated and irradiated thoria-based fuel with high plutonium loadings. We have to properly incorporate kinetics parameters into the codes. As you know, protactinium-233 has a 27-day half-life, and the decay of protactinium-223 inside a reactor gives rise to well-known time-dependent effects. These are well known, but they are not really incorporated into any of into the standard codes that are used, and so that needs to get done, and we are working on that. There are, as I said, a lot of zero-power critical experiments available at CNL. The data is available, and they are being reanalyzed. Some of them are being reanalyzed. Here's an interesting one done sort of in the late 80s or early 90s, and it's been reanalyzed, and it shows thorium-uranium fuel inside so-called hot channels. So these are channels in the Z2 reactor which are under CANDU-like conditions by being artificially heated. And it shows that actually, and it shows it's basically an experiment to look at the temperature coefficient, or the coolant temperature coefficient of reactivity, and it shows that there's a small bias, 3 milli-K or so, which is not so bad, and more importantly that there is, it's flat with temperatures. The bias is flat with temperature, which means that there is no bias in the coolant temperature coefficient that was measured in this experiment. The last topic I'm going to address is proliferation resistance. So thoria fuel has this reputation that it is proliferation resistant because it's got the self-protection, so-called, which is caused by the high energy gamma rays from uranium-232, which invariably builds into a system where you produce uranium-233. If you look at the literature, though, there's no clear indication as to whether this so-called self-protection really leads to proliferation resistance. For a certain class of proliferator who is not concerned with long-term effects on their health and well-being, it really does not pose any problems for them to be able to extract uranium-233. So it just highlights the need for comprehensive approach to proliferation resistance assessments. Another approach that has been suggested in the past has been to do short irradiations and to extract U-233 from the protactinium after short irradiations where there's no time for the protactinium to get irradiated, which leads to U-232 production. So that you can get very high purity U-233, but that's potentially that's the so-called self-protection from U-232 is not available in this case. So so we are continuing to do this sort of assessment for these pathways. Just wanted to show, sort of in the context of proliferation resistance, the Gen 4 International Forum, GIF, Proliferation Resistance and Physical Protection Methodology, PRPP methodology as it is called. Canada and Chalk River, CNL, participated very heavily into that methodology. And using that methodology, it shows some results about, sort of quantitative proliferation resistance studies done for the supercritical water reactor fuel. And in this case, what has been done is looking at the material attractiveness, where the figure of merit greater than 1 means that there's weapons usable material. And you can see on the left-hand graph for plutonium, the figure of merit is less than 1, can only be achieved if you start with thorium-plutonium fuel, because then you're not going to build up any U-238. You don't have any U-238 for the plutonium buildup, so the plutonium continues to decrease. For uranium, on the other hand, the figure of merit less than 1 can be achieved by diluting the U-233 with U-238 by using LEU in the initial mixture. And just as with LEU, the magic number is 20% for being, for not being weapons-grade material. For U-233, that corresponding number is 12%. So as long as you can keep the U-233 content in the total uranium less than 12%, you are not going to, you have proliferation-resistant fuel. Related to proliferation-resistant is safeguards. And we have already talked about this. The U-232, which provides proliferation, so-called self-protection, can also be used for monitoring spent fuel. And again, similar to proliferation-resistant fuel, by diluting, by essentially spiking the thorium with U-238, that can lead to a so-called safeguards by design approach. This is an IAEA term. By mixing the thorium with low or naturally low enriched uranium. Other topics in the Thoria roadmap which we haven't touched about are radiation protection, waste management, reprocessing, and Thoria supply. Just going to leave it where it is. I would say that the Thoria roadmap, the way that we are executing the project is to look for collaboration. So this is a call for people that are interested in solving this problem. We have been developing partnerships with universities, industry, international organizations. An example is the Royal Military College. This is in Kingston, Ontario in Canada, which has been heavily involved in the development of the Thoria fuel models. Somebody mentioned earlier, either in this session or in the other session maybe, is this thorium fuel cycle review by the NEA, the OECD's Nuclear Energy Agency, to which France, US, Canada, Russia, and Germany contributed. This is a very good NEA report which has just come out, and I urge you to read it. It's very comprehensive, very good report. And so that brings me to the end of my talk. The initial, so as far as CNL's Thoria roadmap project is concerned, the initial gap assessment is complete, based, as I said, on Canadian experience and the open literature. The roadmap is in progress. We are addressing many of the gaps, and especially for the next 3 years, we intend on closing many of the science and technology gaps. It is a dynamic process, of course. The status of the gaps changes as we solve them or other information comes to view. And collaborations, partnerships are important enablers, and a CNL paper has been submitted. It's been submitted in the AECL Nuclear Review, which is a journal, a peer-reviewed journal that is published by AECL. And I urge you to look for this paper. It will tell you all that we know about Thoria at this stage. Thank you. I do want to end by giving acknowledgements to some of the many, many people that have contributed to this presentation. Thanks.
Thank you, sir. Are there any questions? We have 5 minutes until 4 o'clock, but I'll take the liberty to go over that if there is enough questions.
All right.
I saw in your presentation this good roadmap for thorium, but my question is slightly different. It is regarding this supercritical reactor, generation 4. So when we talk about fuel utilization for a nuclear reactor, then it is the burn-up which dominates rather than the efficiency. So with supercritical, we are adding more problems, and there may be a lot of improvement in the efficiency. But overall fuel utilization is still like it is dictated by the burn-up. So what is the motivation like for the supercritical reactor design?
I think the burn-up is very high in the supercritical water reactor. We are talking about 60, 70 megawatt days per kilo of...
but that can be achieved without even going for supercritical, like that.
Yeah, but the main reason for the supercritical water reactor is the efficiency is very high. So in addition to the burn-up, the conversion, it's a high temperature supercritical water reactor, so efficiency. And there's also, the supercritical water reactor conforms to all the JIF criteria, sustainability, safety, there's a whole laundry, proliferation resistance, the whole laundry list of criteria it's part of the JIF, Canada's JIF, and it's required to be consistent with all those criteria.
Fine. Thank you.
Hello, Luc van Durpel. Does the roadmap also consider the applicability of your essentially can-do thorium fuels to other reactor systems, being LWRs, SMRs, and if so, well, which ones? Or do you have any prospects of the applicability or transferability of your experience to other reactor concepts?
I think this Thoria roadmap was specific to can-do type reactors, because that's what we know. That's what we know quite well, and that's what we have worked on for many years. So I think that would be the short and simple answer to your question. Obviously, people think about other reactors as well, but certainly not in that much detail.
So you irradiated some fuel elements to very high burn-up. Like we're talking about some 60,000. What was the clad material? Actually, you had gone with what type of clad material for that pellets? Fuel clad material.
Oh, it's Zerk 4, I think. The standard cladding.
So collapsible cladding.
Yes.
But it can withstand so much of burn-up.
apparently I asked the same question. I mean, I'm not a fuel guy, but yes, I was told it's standard cladding.
Achha. So any no design changes are required if you want to go for a fuel cycle with the high burn up for the normal use of such a fuel cycle, plutonium, thorium.
So, correct me if I'm wrong. I'm told that you use the standard cladding, but that thoria is especially good because you know it can take high burn up much better than urania.
Yeah.
You know, there's less release of fission gas, less release of fission products, and all this. But a lot depends on how you make the fuel, and that is why the first gap area, the sort of fuel fabrication, we need specifications for fuel fabrication. This is the first gap. So there have been a lot of different ways in which the fuel has been made, and we need a consistent set of, I don't know, recipes, specifications, rules by which you can make good fuel.
Sir, another question is that if you go for this fuel cycle, advanced fuel cycle using thorium, whether you will redesign your shutdown system or the locations have to be changed or the existing locations are good enough for shut-off rods or any other reactivity devices?
Oh, I think we'll need to adjust those things. I mean, those are engineering. So I think I should clarify that the advanced fuel cycle reactor, AFCR as it was called, which has been more done by the sort of commercial side of the CANDU business, those looked at the engineering questions. What the Thoria roadmap is looking at are sort of the basic science and technology issues, the underlying science and technology issues. But I mean, just because I'm in INC, I can tell you that all that will have to be looked at very carefully and probably redesigned a little bit.
Thank you, sir.
The reactivity control devices will certainly need some careful consideration.
Okay. If there are no further questions, I'll have one.
That's not fair.
Well, it's a real question because I really don't know the answer. In the Thoria roadmap project, do you have any involvement of either Canadian or other CANDU utilities? Do you seek them out as partners to do something similar like it's done in India with insertion of thorium bundles for various purposes?
Well, I think the only power reactor in Canada that we have ever put thoria bundles is NPD. I don't believe there's been any thoria put into any power reactor since then. And so we are, you know, I think the experience in India is excellent. As far as I know, India is the only place where thorium bundles have been put into power reactors.
Thank you. Okay, there are no further last-minute questions. In that case, thank you, sir. And on behalf of the organizing committee, let me thank you and give you our appreciation for coming all the way out here and giving us this talk and contributing to the conference.